Hi there. In this video, I'm going to go over the first of a couple lessons that we're going to do over on statics, or this idea of static equilibrium, or the idea of things that are not moving. So you would have learned in, I guess, in physics last year, and I guess and for sure we've talked about it this year as well. Things that are not moving, where we'd say have balanced forces acting on them. And if they have balanced forces acting on them, it means that they are either moving at constant velocity or they're not moving at all. And so in this idea of statics, it means there's no net force. That means things are balanced. So like if you had an object F1, F2, if this object had balanced forces, then F1 and F2 are equal, or F net is equal to 0. Sometimes instead of writing F net, I do the capital epsilon. So that means sum of forces is equal to 0. So that's essentially what this topic is about, is how can we analyze systems where the sum of forces is 0. And if you had either me or Mr. Davies for physics last year, you for sure have done some of this before. It doesn't mean you remember it all, but it's not a brand new idea. So when we talk about something that's in static equilibrium, there's actually two equilibriums that are happening. One is called the translational equilibrium, another one's the rotational equilibrium. And today's video is about translational equilibrium. So what this means, translation means moving a shape without it twisting or rotating. So that means, like, you know, if an object moves from there to there, that's something that's translating. So if it's static equilibrium, it's not moving in this direction, it's not moving in this direction, and it's not moving in and out of the page. There's no translations. So you know, there's two conditions that are met. So first of all, the sum of the forces has to be 0. And then not only that, but the sum of all the x forces, or horizontal forces, are 0. And the sum of all the y forces, or vertical forces, is 0. So this is like the major sort of the overall encompassing idea of static equilibrium, that the total forces is 0. And then the idea of translational equilibrium is that it's not moving horizontally and it's not moving vertically. So to go over this, I have an example question. A crate is suspended from a beam. So there's my crate, and there's two cables holding it in place. This T1 is 200 newtons. What is the weight of the crate? So we're told a couple of angles and one of the tensions. And our job is to analyze this to figure out essentially what this weight is, or mass, weight. So I'm going to go through one strategy on how to solve this kind of problem, and it's kind of centered around this idea of using vectors and components. So the strategy says, the idea is that we're going to choose one point to analyze, we're going to draw a force diagram, and then we're going to use force components. So what I'm going to do is I'm going to analyze this point right here. That's essentially where all the forces are kind of converging onto. So I'm going to start off by drawing a force diagram of that point. So I have Fg, or weight. I have like this, I'll call this T2, and I'll call this T1. So there's my force diagram, and all those forces acting on that point are balanced. So next thing I'm going to do is I'm going to draw these T1 and T2 as vectors with components. So here's my T1. So there's a T1y component, and there's a T1x component. Likewise, there's this T2. So there's T2x and T2y. Okay. So I'm gonna start off with this idea that I'm gonna choose one of these things to analyze this with, and I'm gonna start with the sum of forces in the x direction is 0. So if the total forces acting at x is 0, that means this T1x is equal and opposite to T2x. They have to have the same magnitude. Otherwise, if it wasn't, this crate would be moving left or right, accelerating left or right. So I'm going to say here T1x is equal to T2x. And T1x is this, let's just check out, that's 55 degrees. That's 55 degrees. So this is 55 degrees here. And this is 25 degrees here. So T1x is T1 times cos 55. And that's equal to T2 cos 25. And I know T1, I'm told that, and I can solve the coses. So I'm going to solve for T2. So T2 is T1 cos 55 divided by cos 25. So T2 is, what was T1? T1 is 200. 200 times cos 55 divided by cos 25. T2 is, pull out my calculator here, 200, 55 cos, 25 cos, divide, 126.6 newtons. So now we know T2. And we're looking for the FG. So now I'm going to analyze this from the vertical standpoint. So the total forces acting Y is 0. So we have T1y and T2y, they're pulling it up, and FG is pulling it down. So we have T1y plus T2y equals FG. All the up is balanced with all the down. So I know everything but FG, so I can solve for FG now. So T1 is 200 sine 55 plus 126.6. Oh, I'm going to run a room. Sorry, it's kind of squished. 25 equals FG. So, and that's it. So I can plug those numbers into my calculator. I'm going to keep this one in my calculator, and I'm going to multiply it by sine 25. And I'll do 200 times sine 55. Add those together, and I get an FG of 217 newtons. And that will be the weight of the crate. And if I want the mass, I divide by F. I can divide by G. So it doesn't ask for mass, but what the heck? 22.2 kilograms. Okay, so that's one way to solve static equilibrium problems with translational equilibrium. So things that are not moving or using components. And this is what you would have done last year in Physics 11 with questions from either me or Mr. Davies. I think in my class, I never did it any harder than having these angles to be the same. I think the hardest question I had would be something like this, 55, 55. So it kind of made it balanced, so it just made the math a little bit easier. Okay, let's take another look at this with a different strategy. So we're going to start off the same point. We're going to do a single point here. We're going to analyze one point on it. We're still going to draw a force diagram, but this time we're going to solve it by using a vector diagram. So the force diagram is the same. T2, FG, T1. Now, we know that all the forces all the vector forces have to add up to 0. So the total forces add up to, that means if I do vector addition, if I draw all these vectors by adding them together, it should be a closed loop. So what that looks like is this. Be something like this. So I'll start with the T1. So the T1 goes like this. It's 55. It's like maybe like, it's a bit too steep. Doesn't matter, but something like this. There's my T1. My T2 is going to go like this, and then my FG comes down like that. So there's my vector diagram of this problem. this angle we know, well, this is 55, so that's 35 there. 35 plus 55 plus 90 is 100. So this is a 35 degree angle. And let's see, what about this one? If that's 25, this must be 65. So there's 65 degrees. And I know T1, but I don't know FG or T2. And this problem can actually be solved quite easily using the sine law. So sine law is, we could just write it out here. T2 over sine 35 equals T1 over sine 65, and then there's this angle there, equals FG over sine theta. And we can actually find out what theta is quite easily, because we know that 65 plus 35 plus theta is 180. So I think when I add that up, I get a theta of 80 degrees. So because we already know T1, we can solve for these other pretty easily. So I'm going to go T1 equals T2 over sine 35 times sine 65. And we already know the answer, but I'll plug in the, oops, no, I meant to do it the other way. I already know T1. T2 is T1 over sine 65 times sine 35. So when I put that in my calculator, so 235 sine, 65 sine, 120, so I get the same answer as before. That's good. And then I'll solve for FG. FG is T1 over sine 65 times sine, so sine theta is actually 80. So 200 divided by sine 65 times sine 80. I get 217. Sweet, same answers as before. So in this one, it's probably a little bit easier to use the sine law if you're comfortable with that. All right, let's try a different one. A 250 Newton weight is supported by two cables as shown below. Determine the tension in each wire. So I'll call this one, I'm going to analyze that point there. Call this T2. Call this T1. This is FG. Let's try the sine law again. I like that, worked out pretty well. So the drawing is very similar to my other drawing. So there's T1. Something like this. And I know FG is going to be coming straight down, so it's going to be something like that. So there's T1, T2, FG. Now, what angles do I know here? If this is 35, then this must be 55. So that's 55 degrees. And if that's 65, this would have to be 25 degrees. Okay. And FG is 250. So I have theta. And so theta plus 55 plus 25 is 180. So it's 70, 80. So this is 100 degrees. Okay. So I have T1 over sine 25 equals T2 over sine 55 equals FG over sine 100. So determine the tension in each wire. So I'll go T1. So I'm just going to solve for T1. So I'm going to multiply this ratio by sine 25. So 250 over sine 100 times sine 25 107. And then T2 is looking at that relationship. So again, it's 250 divided by sine 100. And this time I'll multiply it by sine 55. Oops, there we go, 250 sine 100, 55 sine, 208 newtons. All right, let's try one more here. Determine the weight of this object M. So there's Fg down, there's T1, there's T2. This one's really easily done with the vector diagram as well, because we're gonna get a right angle in there, right angle triangle. So let's do a vector diagram. Fg is down, and T2 is straight across. T1 is up at an angle. Okay. Actually, let me draw it a little bit better, because that should be a really steep angle. There we go, that's better. So if this is 37 degrees, this must be 53 degrees. This is 90 degree, so this must be, and so this one's 37, yeah. And we know T1, and we're looking for Fg. Oh, this is, yeah, so we want to get Fg is T1 cos 53. So it's 50 times cos 53. So it's 30.1 newtons. All right.